Okay, we've talked about liquids yesterday. Talked about gases for 2 chapters before that. We're going to talk about solids today, and that's it. I mean, it would seem like that will be the end of the story. But I am going to go for the rest of this chapter talk about the changes between solids, liquids, and gases. All right, but we'll finish pretty much most of what we want to say about solids today. Okay. Same basic idea that we've been doing. For gases and for liquids, we started out with the kinetic theory description. I'm going to do it again for solids. A lot of demos today, though, after we get past the properties here, I have quite a few things I want to show you. We have a lab on, this chapter doesn't have a lot of labs, but it has 2, I think, or 3.
That's a lot.
Yeah, it is a lot, actually. It's at least 2. And we have a lot of demos today, too, like we had yesterday a lot as well. Kinetic theory description, same basic idea, only this time those particles aren't moving around. They're quite small particles. They are moving. They're just not moving around freely, and there are lots of forces of attraction. They're only vibrating about a fixed position. The intermolecular forces for a solid are much stronger, holding them together. They're cooled down enough. I mean, I could turn a solid into a liquid by heating them up, and I could turn a liquid into a gas by making them go faster. So that's the only difference between them. Basically how far apart, how fast these particles are moving. But they're not sitting still. Even in a solid, they're not, it looks like they are, but they're not. They're actually moving. There's some energy associated with them. The only time all molecular motion is going to stop is if you got to absolute 0, which you can't. There's always going to be some energy there. Okay? Because these intermolecular forces are very strong, they're going to hold these guys very close together. The particles are more ordered. They form a very regular pattern, which we're going to call a certain name. I'm going to show you that. That's what some of my demos are on today. Just like I did with gases, just like I did with liquids, I'm going to talk about the properties of a solid, and you're going to tell me the first one, I'm sure. Remember with gases, it was they had no definite shape, they had no definite volume. These guys, they got them both. Right, definite shape and volume. Liquids had the definite volume, but not a definite shape. Easy properties. I don't think anybody's going to would not know that. But it's amazing when I ask it on a test, like I did with the gases before. People just ask you to list a few properties or whatever. People didn't get them right. Some people left that blank, honest to God. I mean, it's hard to believe, but it's true. Solids are basically not fluids. The particles do not slide easily past each other. Doesn't mean they don't move at all. Doesn't mean there's no movement at all. Or, there is. But, matter of fact, with one of the things I'm going to say, it's going to be surprising probably to you when it comes to diffusion. They have a high density, as we've talked about before. Don't need to spend a lot of time on this. We've done all this before. Much higher density than the gaseous phase. Not much of a difference between the solid and liquid phase, and water's the oddball. Most things get more dense as a solid than they are as a liquid. Water's odd, and you saw the video on that. We talked about that, why that happens, because of the hydrogen bonding. But most things don't do that. They get even more dense in the solid phase. Solids are incompressible, just like liquids. Okay, they're really not affected by pressure and volume changes. That's good. It means I don't have V2, P2, T2, or PV equals nRT. I don't have any of that nonsense to do. That's good in one respect. It's bad in another. That test I just graded for you guys, pretty good. I had a lot of hundreds in every class, and I had, probably the average. I'll tell you what the average is later. A lot of 90s. If it didn't get 100, you had a little mistake here or there. This test, not so much. This test, you're going to have to study for it, as you're already seeing. Because there aren't math problems, because these guys are not, I'm not going to be doing V2, P2, because they don't change with volume, pressure, and temperature. And finally, the one that's a little weird here is that even solids can diffuse. You say, well, if they're sitting there, they're not moving, how do they diffuse? Well, they are moving. So you have to keep that in mind. And it is possible for them to migrate, just not very quick. Right? Okay. And one last one for solids. They have a definite melting point. They change their phase at a specific temperature. True solids do. There are things we're going to talk about tomorrow. We're not going to get to them today. Today's a single today, right? Tomorrow we're going to get to things that are called amorphous solids, things that are not true solids. They do not have a definite melting point. If something does not have a definite melting point, a specific temperature you can point to, it's not a true solid. All right, now I'm going to turn that light on for a second. I'll walk around here with it, and I'll show you all this string I've got inside this. See this? I want you to look closely at this. I got to show it on the video too, because Caitlin wants to see this one. Hannah's here today. What's in there?
Finger noose.
Finger noose. You see anything in there? What's in there? A piece of string. Now I'm going to show this to Caitlin too. Who else is missing? Marie. Marie's never here. What can I say? Check it out. Check that out. There's nothing in there. There's nothing in there.
I see it. There's a piece of
string. Right.
Nope.
Check. What? Y'all watching? Can y'all see from where you are?
He's gonna pull out a dime.
You ready? What? What? Marie would be freaking out right now.
That is crazy.
Isn't that cool? You can't see it. It's invisible. If it was ice, you'd see it. It's not ice.
Imagine jumping in the crack. It's in there. It's some kind of rock.
You watch it again? I'll get closer over here. Ready? What?
Is that toxic?
No. One more time. You see it where you are?
One of those and stick in my shower. Really?
Oh, I can see it. If I get really close, I can see it.
You can see if you put it against the light, you can see the curves.
Yeah, there are little air bubbles sometimes. All right.
The water.
Reason I do that little demo, you can put the light back off, is that's called, well, before I say what it's called, that's called a ghost crystal, and that's what all solids are really made of. They're all made of crystals, and that's what I'm going to talk to you about the rest of this period. We're going to talk about all different kinds of crystals. That one is unique because it has the same index of refraction as water does, which makes it basically invisible. It's just, it has a big long name, but I buy it. It's called ghost crystals. It has a big long name. I don't have it here, but I could read it to you. They have the same index of refraction. You know, light travels at a different speed through air and through water. All right, you probably know that. You probably clean the pool or skim the pool, and when you put the actual skimmer or the vacuum into the pool, it looks like it's broken. Out where the surface is, look, it's broken because light's traveling at a different speed. Well, this ghost crystal has an index of refraction. Its speed that light travels through it is about the same as water, so it looks invisible when it's in water. Now, I always get the crazy questions like, so like if you put that over a submarine, would the submarine be invisible? No, you would just see right through it. It wouldn't make a difference. It's like putting a piece of plastic wrap over. Yeah, you're right. That's what you'd see. If you put that over the submarine, you'd see the people inside. And if you put it over you, you'd see your organs. No, it doesn't work like that. It's not like it makes you invisible. But it is the same index of refraction as water, and that's why it looks like that. But that's a neat crystal to start it out with, but I'm going to show you a lot of crystals. As a matter of fact, we have a lab on that. It's going to be a different kind of lab. And I have to talk about all the different kind of crystals you're going to have to identify. Okay? Let's start out by saying that all true solids are made of crystals. And I have a lot of examples to show you even today, but even more you're going to see in lab. What are crystals made of? Well, they're a repeating structure. It happens over and over again, that it grows. All right, that repeating structure is called a unit cell. Okay? Eventually, it grows into a large enough structure called a crystal lattice that you can see. All right, that you can actually see. All right, that's what it grows into, a crystal lattice. the total three-dimensional arrangement of the particles that these guys grow into. At least it was locked this time. Good job, Haley. All right, now I got a lot of examples to show you. Some you're going to see today as part of a demo. I'm going to grow some. Others you're going to see back there in lab under a microscope. We have all that to do. Probably, today's Thursday, we could probably do that lab tomorrow. I think I'll get through this same notes with Ken with the other class. So we'll probably be doing that lab tomorrow. I have to set it all up. And the stuff I'm going to ask you is going to be stuff like this. I'm going to ask you what type of crystal this is. All right. Now, I'm not going to go so far as to ask you this. You don't have to do not copy this down. If you took a class on rocks, minerals, and fossils and things like that, you might actually have to, in a geology class, you'd have to know all these different kinds of crystals you could see. You know, there's cubic and simple face-centered cube and body-centered cube. I mean, it gets pretty complicated. I'm not going to ask you that. That would become very, difficult, and it's really very specific. There's no real reason for you to memorize this kind of stuff. However, I am going to classify the crystals based on something you already know about. It's another one of those times where you realize how nothing goes away in chemistry. Okay. Oh, by the way, you know what that is? That's a geode. You ever see a geode? You guys ever see those? You may have here's an example of one. Actually, I've got one here. See, a geode is basically a hollow rock-like structure, but inside are crystals, right? And so there's a good example here. You may have gotten those down at Knoebels. Remember that one spot where you have those in that by the mining? It's by the log flume. If you ever went in that building, there's a lot of crystals. There's a lot of neat crystals in there. They're kind of expensive, actually, too, if you try to buy them, because some of them get huge. Look at the size of that one. All right. This is amethyst. Looks like anyway. The purple color is amethyst. I have some of that here too. I got some of these. Small piece of this. I don't know who that person is. I just found the pictures online. See, amethyst. What? What? I'm teaching here on camera. What? I'm on camera. You have to go back later. Come on, what is it about? Oh, not now. That was probably what she wanted to. Shania. All right, look at this is amethyst. And look at it. See, Caitlin? Caitlin can see the amethyst. You're all going to see this close up. Most of these are going to be out here. I'm going to ask you questions. And again, will I ask you the question, what's the name of this? Is this amethyst? No. The kind of questions I'm going to ask you are going to be the type of crystals. Here's a really cool geode next coming up. Look at this one. Look at the size of that thing. That's pretty cool. That's pretty cool. Anyway, I'm going to break these guys down into 4 types. So your job will be tomorrow in the lab, along with a few other questions, possibly on solids or liquids that we've already talked about in this chapter. Your job will be to tell me what type of crystals these are, based on several things. Now, the first type we're going to talk about are covalent network. Remember I said a minute ago, nothing goes away. Nothing goes away in chemistry. You may remember covalent, polar, non-polar covalent, ionic, all that back again. All right, we're going to have to be doing those again right now, determining whether it's polar, non-polar, ionic, using, what did we need for that? Electronegativity charts. Okay, remember the cutoff points? 0.7. No, it wasn't 0.7. It was 0.4, 0 to 0.4, 0.4 to 1.7, and then above. Don't worry, I'm going to go over it all again, but that's what you're going to have to be able to tell me based on whether they're covalent network. Now, covalent network are held together, obviously, by covalent bonds. And this guy, you don't have to look anything up for. There's only 2 I'm going to give you that I want you to actually know. All right, I'm not going to. So if you see either of these, you'll know what they are, and that is diamonds and quartz. Those are very common crystals. I don't have a diamond on me, and if I did, it wouldn't be this big. But you can all see. You've all seen quartz before, right? All right, this is a little piece of quartz. Everybody's seen this before, I'm sure. You're going to see, again, a lot of these will be close up tomorrow in lab. And if you see this guy, you can identify him as quartz. There's not really going to be anything else you could do for this guy. The other ones, the other kind of covalent bonds you could have, you're going to have to subtract and find the difference between them. By the way, there's a better picture perhaps. If you can't see my little thing, you'll see it tomorrow anyway, of course. All right, covalent molecular are the ones you're going to have to do your subtractions for, the ones you're going to have to do your actual calculations for. They're not really much of a calculation, and I'll refresh your memory right now of what they are. Covalent molecular are covalently bonded molecules held together by intermolecular forces, as you'd expect. And for nonpolar ones, the difference, here's your reminder, is 0 to 0.4 again. We had this before, but here it is again. You know what to do. You look at not the common ion sheet, the electronegativity sheet. You subtract the two elements, and you see what the difference is between them. You do not use subscripts. Okay? So, for example, you don't need to write this. If I had, he's not one. If I had H2O, I don't multiply 2 by H, whatever I look him up to be on the electronegativity sheet. You don't use the subscripts. You just tell them the difference between two guys is electronegativity. You actually have homework tonight. You know what your homework is going to be? Make sure you're prepared tomorrow for that lab. You can call that lab a quiz. You really could, because for that lab tomorrow, you're going to have to know the cutoff points. Okay? Not like we haven't seen it before. All right, some examples. By the way, for example, they're held together, the nonpolar ones are held together by those weak London dispersion forces. Remember those? Yeah. It's been a while. I know. There's not much holding these guys together, nonpolar covalent molecules. And so they tend to be pretty weak bonds. And I'm going to use one example I'm going to do for you right here, right now. Right here, right now. I'm going to make some iodine crystals. I'm actually going to do it by resubliming the iodine, by kind of having a sublimation happen. Do you ever know what sublimation is? No. Well, you're going to see it in a second. As a matter of fact, let me set this up here so Caitlin can see it too. I think that might be okay. Let's see. Yeah, you can see that. Can't you, Caitlin? Yes, I can.
Mr. Allen, you can't hear her.
I can hear her. I can hear her in my head. All right, you watching? I'm going to add a little bit. Put the light on so you can see a little better. I'm going to take some iodine crystals, which I have right here. Okay, and they look. It's kind of weird. I'll show you what they look like. They would. Irritate you. Yes, absolutely. You have iodine. What have you used iodine for? We have it in the medicine cabinets. What do you have? Yeah, you have a solution of iodine that you put on cuts. It's supposed to, it's going to not sterilize, but what's the word I'm looking for?
Disinfect.
Disinfect. Good one. Yeah, I like that word. I'll show you this stuff. Kind of looks like, when you put it in here, kind of looks like, ooh, it's kind of in the way there. It just looks like rocks. Yeah, looks like coal, almost. I'm going to put some of these guys in here. They are kind of like they almost look like a purplish color, a bluish purple color almost. It's weird. This is not obviously what you have in your medicine cabinet. You have a solution of this with potassium iodide and water. All right, now I am going to show you how those little crystals in there will do something weird when I heat them up. Okay, I'm heating this guy up, and I don't know if you can see that much of it. Think of the best way to do this. I don't want to have to take it off again. I know. Oh, I'm so smart. Oh, look at that. Now, check this out. Oh, you know what I almost forgot? Oh, I need an ice cube. Do you see it right there? Could you run down and get me an ice cube for just a bag of ice in the nurse's office for a second? I forgot. Oh, it's already happening.
It's for science.
It's for it's for science. It's already starting to happen here. Can you see there? I know I can see it on the camera there. Notice the purple haze like Jimi Hendrix. The purple haze. Oh yeah, my shirt. Yeah.
His purple haze was different from your purple haze.
I think his purple haze was a lot different than my purple haze. Yeah. Well, I want to get the ice on there because I don't want those fumes to really get out. They are annoying. Not as annoying as I am, but they are annoying, and you don't really want to breathe them. You just need Brandon to hurry up with his ice cubes.
Mr. Allen, we're not going to be here tomorrow.
Well, you'll miss a lab, but I can. That's actually a lab I can actually make up because I'll show you how we're going to do that. Well, I'll talk about how we're going to do it. It's different than a normal lab. Good job. All right. Now let's get some ice cubes on there so we don't be breathing the fumes in before I keep heating it. Because what will happen is that's sublimation. Notice that iodine, instead of turning into a liquid, is turning into a vapor directly from a solid to a vapor. I'm going to heat them up again a little bit more. Okay? You see that? Vapor there? The purple, again, my purple shirt's in the way. Why did I wear purple today? That was pretty stupid. All right, can you see it now? All right. Now, it doesn't take much. Notice, it does not take a whole lot of energy to do that. All right. And what's going to happen as I'm doing this, those vapors are going to travel up. And when they hit the cold watch glass on the top with the ice there, what do you think they're going to do? They're going to recrystallize that. It's called deposition. All right, and those are the crystals you're going to look at tomorrow. They're going to be one. I'll guarantee you're going to see this same jar. They're going to be one of the things you're going to see tomorrow when you are back there, and you'll be asked to identify them. Now, how will you know iodine is a nonpolar covalent molecule? Because what's the difference between I and I in I2? 0. Right. And if you look up CH4, if you look up sulfur S8, they're 0. If it's just one element there, the difference between him and himself is 0. Okay? I'm going to need some. Jackson, can you give me beaker tongs to get this out of here? Yeah, you're going to find, by the way, that's something you'll be able to see a lot better. I'm going to show it to you a picture on the thing up here in a minute. But tomorrow when you're back there, you'll be able to see a lot better how there are little stalactites up there, like Brendan said. Yeah. Put that few one on for me for a second and open it up for me. I'm going to move this out of the way because we got to keep teaching. And I'm going to show you what happens also. Caitlin won't be able to see this, but I'm going to show you what happens when I take the lid off. No. Open it up. Yep, open it up. Get out of my way. Come on, hurry up.
I'm sorry.
Don't hit me. Don't knock me down, Clark. All right, watch. This is pretty cool. If I take the lid off, you can't see, stand up. I take the lid off of this, you'll see the fumes just kind of leave. See? But it's in the fume hood, so it's okay. And if I look at these guys underneath, notice you can't see it from where you are, but you will see it tomorrow, and I'm going to show it to you right now on a picture of what it looks like. Okay? Turn that front light off. All right, let's put this guy back. No, that was only the first demo. Or second.
Way more than that.
We have way more than that. All right, let's take a look where we left off here. So, take a look. Iodine looks like, that's what you're going to see. Put the light off, you can see it even better, I think. You can see the iodine crystals are going to be growing like stalactites from the top of that watch glass. You see it? That's what it's going to look like tomorrow. If I ask you that guy, if I ask you this guy, you have to be able to know who's who. You actually have a little bit of studying. I don't normally do this, but I'm telling you, there's basically a quiz tomorrow, and it's going to be just a matter of studying. There's no homework. I haven't had any homework yet because there's no math to really be doing here. So this is one way I'm going to keep you from you know, to keep you up on the stuff, basically. All right, you get that front light back on, back light back on, and you can turn the fuel light off. All right,
Might die.
close it down all the way though, just in case.
Oh,
Your tongues are so.
You can move it. Careful, don't hit the beaker though. There you go. All right. Those crystals under a microscope would look like that. They're kind of cool looking. And again, there will be several microscopes back there. You'll be observing crystals, and I'll tell you what they are, and you'll tell me what kind they are. Okay. So far we've seen covalent network, covalent molecular nonpolar. I also can have covalent molecular polar. Let's look at those. Okay. The polar ones, still crooked, but whatever. The difference there is 0.4 to 1.7. Those are the numbers you had to remember for that one. Okay, they're held together by dipole bonds or by hydrogen bonds. And the way you'll know a polar crystal is by looking that up, the difference between the two guys. So you subtract the two elements that hold them together. If it comes out to be between 0.4 and 1.7, you know he's a polar bond. Therefore, he's a polar crystal. Some examples of that would be water or ice, like that kind of crystal, like a big snowflake, right? And ammonia. If I look those two up, and if I have ice out there tomorrow, you want a prize with that? All right. Voice is cracking. You want to look up the difference between them. You find that he's polar. Ice would be an example of that. Ice is water. That's the formula. All right. What else we have? Well, we had covalent network, covalent molecular nonpolar, and polar. We have metallic crystal. I'm going to show you a little demo of that one. Show you this little demo here. Well, before I show it to you, I guess I should give you the notes on it. You remember what the metallic bond looked like? You remember that? Again, a little bit of a review. We've seen this before. It was the positive ion surrounded by a sea of electrons. All right, like this. Remember this? I showed you this, and I had a little animation for it, and we had a video for it. It explained malleability and ductility, and remember that? And conductivity and luster were all explained by those positive ions who have lost their electrons and forming this glue or this sea of electrons that holds everybody together. Okay? So, that was the metallic bond. But it grows into a crystal. And I can show you those crystals. Again, you will see this much closer up tomorrow. One of them out there will be this guy I'm making right now. Here's what I'm going to do. Take a look. Check it out. Put that light on again in the front. No, not really. It's very light. Because all this is like copper tinsel, I'm going to take. And this is kind of interesting. Because what I'm going to do is take a little bit of this copper tinsel. I'm going to put it into a beaker. Okay. See it there in the beaker? Now, copper itself, you leaving?
Yeah. I'll get the rest of the
Yeah, there aren't many more left, but there's a little bit more left. Put a little bit more in. Making a mess. And copper itself, if I just had a piece of copper out there, is actually made of God bless you, of metallic crystals. But I'm going to do something beyond that. All right, if you look here, I'm going to add some silver nitrate to this. Remember silver nitrate? This bottle? The stuff turns your hands brown. We'll pour some of this in here. Now, you're not going to see much happen immediately. I want you to just look at this real quickly. You're going to see this a lot better, a lot closer up tomorrow. Why won't that focus on there? Well, whatever. You'll see this a lot closer up tomorrow. But look at it now. It looks like copper. I'm gonna come around with this in a second while I'm getting the rest of these notes, and you'll see it looks a lot different in a few minutes. It's not going to catch on fire. You can't eat it. All right. So we're going to come back to that in a little bit. Get that light off for me. Okay. So that's metallic crystals. We'll come back. We'll see one of those in a second. But before we do, this is what you're going to see under a microscope tomorrow if I show it to you. Okay? These are what they're going to look like. They're really cool looking. And if you get a chance to see them, you'll see that tomorrow. The fourth one, I told you there are 4 types. Ionic crystals, where the difference is 1.7 or greater. I'm louder. Anyway, so 1.7 or greater, going to be ionic. They're held together by the positive and negative charges of the ions that are formed. Remember, one guy loses, one guy gains an electron. You know this. You've been writing ionic compounds for the past 3 months. Okay, ever since we first taught it to you back under just getting formulas after the end of the periodic table chapter. And then we continue to do them throughout reactions and then stoichiometry. Anytime you write an equation, you're writing ionic compounds, usually. We're using a lot of ionic compounds. What's our most classic ionic compound, I would hope you all know? Salt, yeah. Sodium chloride. So if I have salt crystals back there, you're looking at them under a microscope, what will they look like? Well, they'll be cubic. You'll see they look like cubes. But it doesn't have to be salt. It could be any 2 guys who have a greater difference of electronegativity than 1.7. Any 2 elements that get together like that, you could tell that's an ionic crystal.
What's CaF2?
Calcium. What is it? You tell me. What is it? No, it is not calcium difluoride. It's calcium fluoride. Why do I not have to say difluoride? Because it's not 2 nonmetals together. It's a metal and a nonmetal. All right. But if you were to look up the difference between these guys, between Na and Cl, it's greater than 1.7. Between Ca and F, it's greater than 1.7. And you will have, back there with you, at those stations, you're going to have your electronegativity charts to be able to do that. Okay. Oh, I'm not doing that one today. I want to come back to this one because you're going to see a big change. I don't know if it's better to have a white background or a dark background for this. Let's take a look at what you can see. Well, my shirt is dark right now. Ah, look at the difference. I'm showing it to Caitlin first. There's not much of the copper left. It's kind of turned into silver. What? Silver? Yeah. Look at
Silver nitrate.
yeah, don't touch it. Remember, it will turn your hands around, but I'll pass it around and you can look at it. Gently. Don't spill it.
Shot of silver nitrate.
Look at it. What was the reaction I did there? What did I add together?
Silver nitrate.
Copper plus silver nitrate, right?
Yeah.
And what did I get?
Copper nitrate.
Copper nitrate plus silver. Now, I do have to use charges. This guy's a +1, he's a -1, so he's written correctly. But this guy's a +2, he's a -1, so it's copper nitrate like that. I'd have to balance them. I would need a 2 there and a 2 there. Got it?
Drink it.
Yeah. Don't spill it. Be careful. And don't mix it up too much because all the little crystals fall off. Okay? So my question to you is, what's that silver-colored stuff on there?
Silver.
It's silver. It's real silver. You want to know why this is so expensive, the silver nitrate? I tell you not to spill it. Okay? Because it's got silver in it. All right? So it's expensive. I was looking to buy a bottle of, for next year, and I think it was like...
Does it hurt, like, when it turns brown?
No, not really. I was looking to buy one, and it was... I'm basically not, because it was depending on the concentration, it was like $150 depending on for a bottle of silver nitrate.
That big?
Well, no, like I said, it would depend on the concentration, and they're usually 500 milliliters, which are about that big. No, obviously not.
Can we turn that to silver?
What's that? All right, now I got to give you your test grades back too.